All right, first question. Did I ever make a correction? In problem set 5, there is a very important gap right there. Did I ever give a number for it? All right. So now you know. So it's 120 meters of fishing line. If you go back and look at the lecture where I do the Fish of Fury problem, everything else should be straight and forward. I know that on Blackboard, problem set 5 has the same page on front and back. It really is only this. Or, oh, crud. I take it back. There is something more. But we don't have time right now to talk about it. I'll make an announcement later. Problem set 6 is now available. Problem set 5 is due on Thursday. Problem set 6 is due on Tuesday. And what we will do is talk about stuff for that. Oops. So now here we go. All right, what I've been trying to do is, for the last couple of weeks, introduce the idea of rotational motion. And motion can come in the form of linear and rotational. And now, what I'm going to do is I'm going to show how energy will do the same thing for linear and rotational motion. Energy can help us explain how high balls get when you throw them up in the air, the velocity at particular points. They have a certain distinct advantage. In energy, there is potential energy and kinetic energy. Potential energy has the ability to do stuff. Kinetic energy means it is doing stuff. Now, potential energy, I believe we've talked about some of it. There's gravitational potential energy, and I like to write it shortened potential energy like this. Gravitational potential energy is mgh. If I have an object and I'm holding it a particular distance above the floor, here it has the same potential difference as it does over here, but this one has a lower potential energy, this one has a higher potential energy. Like there may have been, I think there was that time where I held a book over people's heads and dropped it, and, well, I didn't actually drop it, but what causes a greater amount of pain? I could drop it from a higher height, or I can get a bigger ball. And so the higher height is the bigger H, the bigger ball is the bigger M, the potential energy is the amount of energy doing stuff. There is spring potential energy, which is 1/2 kx squared. Now, spring potential energy comes from springs. And just as a quick review, with springs, if you have a spring with a mass, and this particular, let's say there's no gravity at the moment, if you have a particular mass at a particular distance, there's a point where the spring neither pushes nor pulls. So like if you have a spring and you just let it go, it'll end up at its rest location. And if you push on that spring or pull on that spring, there is a displacement from that rest point that we'll call x. And when you compress the spring, obviously you can feel it push. When you pull the spring away, you'll feel a pull back to its rest location. For cases where there's a push or a pull and x is the distance at which it is pushed, there is Hooke's law, which says that the force is negative kx. Now really how it's written is the force vector is equal to the negative of k times the x vector, where x is the displacement. So really, if I was going to write x as a vector, it would either be that way or that way. And what this really says for Hooke's law is that the force, its direction is always opposite of the displacement. So if you push it to the negative side, the spring is going to try to push it to the right, and vice versa. So this is the whole thing about Hooke's law. The way that I typically write Hooke's law is for 213, we use just F mag, the magnitude of the spring is equal to kx. And so the question is, what is k? K is the spring constant. You have springs that when you look at, you go, well, they're kind of thin. They're not going to pull real hard when I push them or pull them. And so I can move it around however I want. And then you've got, like, if you've ever looked under your truck, you've got the suspension springs. Those things have really high K values. It would require a lot of force to compress those springs. And so you can think of the spring constant as the strength of the spring. The units, if you just solve for K, F over X is equal to K. F is typically used as newtons, X is in meters, so the unit of K is expressed as newtons per meter. And it is dependent on the type of spring. Some springs have high Ks, other springs have low Ks. I'll give you the K, or you'll have to solve for it, basically. And this K goes in here. So the spring potential energy is 1/2 times K times the displacement squared. So you take that distance, square it, multiply it by K, and then divide by 2. Where does the half come from? Calculus. So we won't go into that. These are the major types of potential energies that we're going to deal with, and they are for linear Well, in a way, they can be used in linear and in rotational. I'm sorry. The kinetic energy you have a linear kinetic energy, which is 1/2 mv squared And then there is a kinetic energy rotational, which is 1/2 I omega squared. And we've discussed the differences between these two. That linear mass becomes rotational mass, which is moment of inertia. Kind of like the difference between the pin and how you rotate it this way and the difference between rotating it that way and rotating it this way. Velocity becomes angular velocity. And so you can have, like if I throw this ball and I put, if the ball only moves like this, so it only moves from left to right, it has a linear kinetic energy only. So you write down it's 1/2 mv squared, and that would let you know how much energy it had. If it was just simply rotating like that, it would have a pure rotational energy. If it sits and rolls like that, it has a rotational and a linear thing. In these types of problems, since we're just still in the wading pool with our little floaties, the motion that we'll be dealing with is primarily either all linear or all rotational. We're not gonna mix it up. So there are different ways of expressing energy. Gravitational, spring potential energy, you have linear and rotational kinetic energy. How can we put this stuff together in order to do stuff? Now, one of the concepts that we need to get or understand better is conservation of energy. So the way that I learned it, the professor that taught me basic physics, is he sat there, or he brought, well, he used tennis balls, but I'm just going to use pins. And let's say these are the only 5 pins in the room. And so I put them now on the table, and I go, how many pins are in the room? 5. All right, now I'm going to take one of these pins and I'm going to put it over here. How many are there in the room? 5. How hard is that? But I'm going to take, I'm going to take this black pin and I'm going to put it in this drawer. And I'm going to close the drawer. Now how many pins are there in the room? 5. 1 there, 3 there, 1 in the drawer. So conservation of energy says that the system, the energy doesn't change. So if you've got 5 pins at the beginning, you're going to have 5 pins at the end. Now, how do we change the number of pins in the room? Take one of the pins, throw it out the window. Or take a pin and smash it, destroy it. Or mostly put it in the garbage, let the janitor take it out the next morning. So if energy leaves the room, if the pin leaves the room, then the number of pins change. So in conservation of energy, the energy initial is equal to the energy final. That if you have something that, if I go energy is conserved, you go yes, because the beginning of the energy is the same as the end of the energy. When is conservation of energy not, probably better word, doesn't happen? When you change the system, namely the biggest source, if I say there's friction, Remember how I used to say earlier when I mentioned there was that summer class and I had the students trained, and whenever I said there's no friction, everybody went, yay, no friction. This is one of the reasons why. If there is no friction in the system, yay, no friction, because now you can say the conservation of energy is true. If I go, there is friction, boo, there's friction, then that just means that the energy initially is not equal to the final energy. And typically, well, if there's friction and there's nothing entering the system, energy initial is greater than the final energy. There's another reason why or how energy can leave the system, and we'll get into this in a little bit, is inelastic collisions. In inelastic collisions, you can definitely say that the energy initial is not the same as the energy final. We're going to get into that in a little bit. So let's first do a simple problem where you have a mass with gravity. The height is 10 meters. The initial velocity is 0. I want to know the velocity the moment before impact. Simple, drop an object, have it fall. What's the velocity at the bottom? That's all I need to know. Well, if you were doing it with motion, you would first have to go x equals x naught plus v naught t plus 1/2 at squared, and v equals v naught plus at. You would have to set up the origin. You would have to set up direction. I'll set down as positive. X naught and v naught are all 0. A is positive 10 because it's down. So 2x over a is equal to t squared, or the square root of 2x over a is equal to t. Then, the reason why I couldn't go straight for velocity is because the velocity has an unknown, the time, which I've just solved. So v is equal to a times the square root of 2x over a. Now watch what I do now, because this is just a good technique to know. A becomes square root of a squared. This becomes 2xa squared over a. One of the a's cancels, and I'm left with the square root of 2xa. So now I can figure it out. 2 times 10, which is the height, times the a, which is that, and so it's the square root of 200, whatever that is. I'm not interested in the specifics. So that is how we normally solved for the velocity for a drop. There's a set procedure. When I initially started teaching, I of course picked these equations as Dr. Eschenberg's favorite equation and Dr. Eschenberg's second favorite equation. It was I almost chose other equations to be my favorite, which are the energy equations. Here, now granted, there are little things like, hold on, question, yes. Oh, this? This is the velocity equation of motion equation. T is the square root of 2x over a, and then I substitute. From there to there, a is the same as the square root of a squared. Because what's the square root of a squared? A. So the reason why I did this is I could stop right here and plug it in. But what I like to do is get the final equation in a more simple. Here you've got a number and 3 letters. Here you've got a number and 2 letters. I just like to simplify it. And it is useful for problem solving to occasionally do that. Now, in the dropping of the object, is there friction? No. Yay, no friction, because I can immediately write energy initial is equal to energy final. Energy problems are way easier than motion when determining velocity. If I ask for the velocity at the bottom of a drop and you go, am I more interested in solving for the final velocity or the time of flight? And I go, you want velocity first. Am I required to do it in any specific way? No. Pick your poison. You go straight for energy. I appeal to your sense of laziness. The energy is the best way to go. The key is to ID the energies at the beginning and end. I don't care what's going on in the middle. All I care about is the beginning and the end. As I think I've done before, since everything before spring break is fuzzy. Is the potential energy here the same as the potential energy there? Yes. What was the change in potential energy there? Nothing. But it went down. I don't care. Only the beginning and the end. What if I do that? And you go, well, is the height still the same at the beginning and the end? Because I got a little confused. And I said, yes, they're the same. 0. So the change in potential energy. And it's also one of the things in my pedagogy, I look like an idiot, and then it reinforces it in your brain. So when you sit there and go, what are the potential energies of this state? You'll remember my just spasming in front of the room. At the beginning of the motion, yes?
Why did you get 2x over a on the position?
I solved for t over here. So that just went into there. It was a substitution. Okay. The energy initial, technically you write this. Oop, not that. Energy, total energy, is the sum of potential energy plus kinetic. If you have a particular state, it's moving, or it has the potential of moving at the time. It also has the potential of having a potential energy. In this simple example, 2 of the 4 terms can be 0. Which goes back to my whole idea of I don't like numbers, and someone said, you do have a favorite number, and I said, how dare you, name it, and they said, your favorite number is 0 because it takes away stuff. And I go, fair enough. 0 is your friend. 2 of the 4 on this equation at this moment for this problem are 0. Which 2? Correct. At the beginning, I specifically said it was dropped. The initial velocity was 0. If the initial velocity is 0, the kinetic energy is 0 because 1/2 m0 squared is 0. The potential energy at the end is 0 because the x-coordinate here is 10 and the x-coordinate there is 0. The final height is 0. So I'm left with potential energy initial is equal to kinetic energy final. Potential energy initial is just mgh. The kinetic energy final is 1/2 mv squared. My m's cancel. One of the things that you don't have to know in this particular type of problem is the mass of the object that's doing the motion. It is mass independent. And now 2gh is v squared, square root of 2gh is equal to v. So this is square root of 2 times 10 times 10. Square root of 200, same thing. So when you're dealing with problems where I ask for 2 conditions. 1, I'm looking for velocity, and that's the only thing I care about. And 2, I give you permission to solve it however you like. You attack it with energy, because energy is the fastest way to do things. All right, next. What we're going to do is we're going to introduce friction. Now we all know about what friction is. Friction force is mu sub k times the normal force. And what we have talked about, I think we've talked about before, is work, energy as work is force times distance. Work is, you could put energy into the system. I take this ball and I lift it up a particular distance and I've done a total amount of work. mg was the force, distance was the height. So the total work that I did was force times distance, or mgh. In this, we're going to deal with the problem of a mass, which is 5 kilograms, is initially moving with a velocity of 20 meters per second. It encounters an area of friction, boo friction, and it stops after a particular distance. What is that distance? So it's a lot like this book bag. I push it and it comes to a stop after a particular distance. Why is that? Because there's friction between the book bag and the table. There are little bits of the book bag latching onto bits of the table, and they're just rubbing up against each other and snapping off. Another way that you can tell that energy is being transferred, we've all done this. Take your hand on a surface that can have friction and then just start rubbing. After a while, what happens? It gets hot. The energy from your hand, that motion, is rubbing up against, or the hand is rubbing up against the table. It's producing heat. Energy is leaving the system. And so what happens here is that the object on the surface is rubbing up against the the mass, and heat is created, energy is released. When friction is in play, the energy equation looks like hold on, don't write that. Trying to the energy that you start with minus the energy pulled out by friction is equal to the energy that you have at the end. A lot of time, there are different ways that people write this equation and explain the variables, but this is how I equate it. The explanation would be different to 211 students. But I think the 213 explanation is more simple and straightforward. I call it the bank account equation. The amount of money you have at the end of the day, E final, is the amount of money that you have at the beginning of the day, E initial, minus the money that you spent. So if you started with $10 and you spent $2, how much money do you have? 8. That's how easy it is. So this equation becomes, now we got to start thinking about this. The energy initial. What is the energy initial at the beginning? Was there potential energy? Now technically, if there was a hole way over here, you could measure the difference between there and there. But if the height, or if the H initial is equal to H final, the potential energy is irrelevant. And if I see a flat surface, I don't even think about potential energy. In fact, I don't see a spring, so there's no spring potential energy. We'll eventually do one of those. I see no change in height. It's a flat surface, so there's no gravitational potential energy. So there's no potential energy whatsoever. The initial energy is entirely kinetic. It's moving. So the initial energy is the kinetic energy initial. Now this is the work, the energy removed, pulled out by friction. And then, what is my final energy? What's the final energy of the system? 0. How do I know it's 0? The velocity is 0. There's no height that's not hanging over anything. There's nothing there. So that is 0. Now, because we're dealing with a flat surface, we do our normal ritual. Some of the forces in the vertical are 0, which means F minus mg, or normal force minus mg. So normal force is equal to mg. And then friction force, which is defined as mu sub k Fn, is equal to mu sub k mg. The work, which is force times the distance, is the force, friction force mu sub k mg, d is the distance. So now we've added an extra step. Earlier we just found out what friction force is. Now we're using friction force to determine the amount of energy removed from the system given a certain distance. So this equation becomes 1/2 mv squared minus mu sub k mgd is equal to 0. So 1/2 mv squared equals mu sub k mgd. And once again, the m's cancel. One of the reasons why I do this, and I repeat it because it's so important, to use these energy equations, if you want, you can pull that blind up so it doesn't rattle. I do this with letters because it makes things so much easier for you. Because if you can solve it generally like this, I could ask for V. I could ask for mu sub k. I could ask for G if you're on a different planet. I could ask for D. You know basic algebra, you could solve for any of the variables. It doesn't matter which one. So this becomes V squared over 2 mu sub k G D. The V was 20. This is 0.2. G is 10. So 20, 40, 400. I think it's 100. Oh no, it's not. Maybe I'm right. I'm still right. Divide by 10. Divide by 0.2. Yes, I am right. So it traveled 100 meters before it came to a stop. And this problem could be rearranged into, given these conditions, it traveled 100 meters, what was its initial velocity? It traveled 100 meters with an initial velocity of 20 meters per second. What was mu sub k? You're on the planet Krypton. It traveled that distance with this coefficient of friction. What is gravity on this planet? It doesn't matter because you've got everything here. And once again, it's mass independent. I didn't need to give you 5 kilograms. Like we've talked before, second test, now it's a rematch between you and me. If I had not given you 5 kilograms, if I didn't give you the mass, and I simply asked the same question, give me the final velocity, and you asked the question during the test, you didn't give us mass. What's up with that? And I go, it's a correctly constructed problem. I'm telling you, I can't tell you that mass is not relevant, but I am telling you that mass is not relevant. So you should know that if I didn't get, it is becoming, there's always mistakes, I admit that. But in terms of glaring mistakes like forgetting to give you mass or forgetting to give you the length of the string, like in this, in a testing environment, I'm really good at trying to figure out that all the numbers are there. And it falls into 3 categories, and I'll restate the categories. Numbers given because you need them. I mean, you can't do the problem if you don't have them. Numbers not given because you don't need them. And then the third category, numbers given that you don't need. If I assign this as a test problem and I saw you flinging 5s around there and masses and trying to cram that 5 into the problem and you still got it wrong, I know you really didn't know what you were talking about, because 5 was a dead end. 5 was, I wouldn't say it's a trap number, but it's a number that helps me see if you understand what's going on. All right, next. Right here, we have a spring, and the spring has a constant of 200 newtons per meter. The mass of the object is 8 kilograms. At the height of this, I'm trying to figure out if this is going to work where the numbers are working out nicely. 20 meters per second. Let's go with the straight up conventional. I want to know the velocity at the bottom if the compression distance is 0.5 meters.
Did you mean to put 20 meters per second for the height?
No, I did not mean to put 20 meters per second for the height. 20 meters. Okay. I want to know, and actually I'm going to write VB and VA. A is uncompressed. At top of hill. B is uncompressed at bottom of hill. Now the first thing that I go, if you saw this, and the question that would be hitting me is, where's friction? Please tell me there's no friction. And I go, there's no friction. And I go, yay, no friction. So the mu sub k is 0. Now if I know if the mu sub k is 0, that means the energy at the beginning of the motion is the same as the energy at the end of the motion, and also it's the energy in the middle of the motion. So the energy initial will be the same as the energy there and the energy at the bottom. So all of those energies are the same. Now, here, we're going from the initial to A. Initially, it's compressed. Initially, it's at the top of the hill. At the end, it's still at the top of the hill, and it's also, but it's uncompressed and moving. The initial energy is, we've got potential energy. We've got potential energy of the spring, potential energy due to gravity, the energy at A, the uncompressed, is the potential energy for gravity plus the kinetic energy at A. These are equal. There's no change in potential energy. In fact, when I'm doing something like this, there's no difference between having a problem where you've got this multi-level and I say, we'll talk about the spring at the beginning versus, oop, is it gonna focus? I don't think it's gonna focus. Where you're only thinking about that part right there. There's no change in height at the very beginning, so you could just forget about it. And you can also see that the equations disappear, and so you don't really care about it. So the potential energy of the spring, 1/2 kx squared, is equal to 1/2, oop, so this is velocity at A. Hold on. And so the velocity at that particular point, ooh, that's good. 12.5. meters per second. That's the velocity at the top of the hill. Now, what I'm also interested is what's the velocity at the bottom? And we can go from A to B. Energy at A, energy at B. Energy at A is both kinetic energy at A plus potential energy at A. Energy at B is only kinetic energy at B. There is no gravitational potential energy. Doing energy problems, it is critical to understand the energies at the beginning and the end of whatever problem you're working with. If you can set that up correctly, solving it is easy. 1/2 mVA squared plus mgh equals 1/2 mvb squared. And now we just solve for VB. And once again, by doing it in alphabet soup mode, you can solve for any of the variables. First thing I notice, m in every term, drop that out. Solve for VB. Multiply both sides by 2. VA squared plus 2GH is equal to VB squared. So VB is the square root of VA squared plus 2GH. So 23.58 meters per second. Yes.
Isn't VS 2.5?
You mean this?
Yeah, because 200 divided by 8 is 5, and then the square root of that is 5.
200 divided by 8 is 25. Square root of 25 is 5. Oh, thank you. 2.5, and that changes that to 2.5. Thank you. And it helps to have so many people doing the calculations along with me. So then that just changes it to 20.16 meters per second. Yes? What I did when I went from there to there, good question, I multiplied both sides by 2. Two attacks that, they cancel. 2 attacks that, it becomes a 2. And so that's where the 2 comes from. And again, another advantage of the alphabet soup method, he recognized that I did a math error. And so what I could easily do is substitute that number and propagate it through because the equations are unaffected. The letters were correct. The other thing that you could do is you could do a unit check. You could look at this equation and go, I don't know if this is right. Well, VB is in meters per second. Velocity squared is meters squared second squared. I don't care about numbers, they're unitless. Gravity is meters per second squared. Height is in meters. This becomes meters squared second squared plus meters squared second squared, which is meters squared second squared, which is meters per second. It works. So you could do, now if we were really getting odd answers, one of the things that I would definitely do with this is start unit checking. Because if I did this and I ended up with meters per second equals the cubic root of meters per second squared, I know something's wrong. So doing unit checks really helps. All right. So with this whole energy thing, one of the things that we do with it is, well, we collide stuff. And with collisions, I mean, a simple collision is you have a ball on a table, or bowling. Bowling is a type of collision. There are 2 forms of collisions. There's inelastic and then there's elastic. Elastic collisions, inelastic collisions. Elastic collisions are rare. Inelastic collisions are quite common. To double check problem 6. All right, everything is inelastic. Good. In inelastic collisions, momentum is conserved. In elastic collisions, momentum is conserved. In elastic collisions, energy is conserved. In inelastic collisions, energy is not conserved. Gee, Dr. Eschenberg's doing a lot of highlighting. What could that possibly mean? Energy is not conserved in an inelastic collision. Energy is not conserved in an inelastic collision. In an inelastic collision, is energy conserved? No. Now, I've now said it 3 times. It is binding. If anyone on a test, on the final, on a problem set, when they're on the bus and they start conserving energy in an inelastic collision, I will start to nervously twitch. There are certain things that Eschenberg students do, and you guys go, wow, he's pumped up right now, because I'm trying to help you. If you start conserving energy, that's the equivalent of you just dancing off into the Velociraptor pit. It will eat your face. And then you don't come back whining to me about this. Inelastic collisions are what's going to be on the test. Elastic collisions will only be in multiple choice, other than the fact that you know that elastic collisions conserve energy and momentum. I've double checked the problem set. Some years when I'm feeling particularly angry, I give you an elastic collision problem and I say to solve it. And then you come back with like multiple sheets of paper and go, this was just a hateful, spiteful thing. And I say, yes, it's to teach you to appreciate inelastic collisions and be happy you don't do elastic collisions. Elastic collisions take a lot of time and are just, it's not the real world. Inelastic collisions are everywhere. An inelastic collision would be me throwing a ball, you throwing a ball, they come together and stick. If you see the word stick or change form, you're dealing with an inelastic collision. An elastic collision, I've only seen one good example of an elastic collision, and I'm not going to talk about it. Something that is close to elastic collision, which means it's still inelastic, but it's probably as good as it gets. Pool balls colliding against each other. Like if you shoot pool, they hit, and the reason why they're truly inelastic, what happens when you hear, or when you see, I gave it away, when you see balls colliding, you hear them. If you had an infrared camera on them, you would see a small amount of heat released because they are making contact and they're grinding together a little bit. So heat released, sound created, these are the main things. Changing form is a big source of where the energy goes. In the example that we typically do in inelastic collision problems in my class, we do cookie dough, because cookie dough, when you throw them against each other, they typically stick. And some people love chocolate chip. I like oatmeal raisin. But hey, we're all different. But when you take big balls of cookie dough and you collide them together and they stick, what's the one thing that you know that happens? They move. They change shape. Each ball becomes kind of like a hemisphere, and they're stuck together. So you've got two balls and then they collide and they're like that. If it goes from that to that, it changed shape. How do you change its shape? You spend energy. So for inelastic, the momentum initial is the same as the momentum final. And just as I'm looking at this, since I'm doing this problem, on problem set 6, I want you to take out number 3, these 3, and then I want you to take out number 11, because we've basically done that stuff. Take out problem 3, on page 1. Just to speed things up in number 11. Because what happened was, what I've just recognized, there is a second page of problem set 5, and I'm going to give it to you tomorrow. But one of the things that we're going to do is, for Thursday, you're only responsible for page 1 of this. There are 3 torque bar problems that I want you to work over and have them turned in by the next Tuesday. And don't worry, we're going to do those at the tutorial. So it's not going to be a big deal. All right, so what we're going to do is a simple inelastic collision, and then we'll be out of here, or we'll play with it for a while. Oh, a couple of things. This is what we're going to do. This is the Molly Dolly Panda problem. This was given as a test problem. There was no one asked for it, but I did a panda theme test one year. Molly is a panda. Her twin sister Dolly is at the bottom. They have not seen each other, so Molly, who has an initial velocity of 0, and Dolly also has an initial velocity of 0. Molly comes sliding down the hill and then slams into Dolly, and then they hug. And then they continue on sliding. Is there friction? No, no friction. Yay, no friction. Now we're going to do a little bit of an IQ test on the class. Molly's mass, it's a panda. I don't know what masses of pandas are. Let's just say it's 100 kilograms. It's a big panda. Do you know what the appropriate mass of a panda is? I'm not sure either. Let's just say 100. But I know this for sure. Dolly is Molly's identical twin sister. Let me say that again. Dolly is Molly's identical twin sister. Exactly. What's the mass of Dolly? 100. I tell you the truth right now. I didn't give this mass. I just said they're identical twins. And then I had people ask me during the test, well, maybe she had a sandwich. Are you sure they're exact masses? And I'm like, they're identical twins, really. We have to go through this. So, they're identical masses. She comes down, collides, then they stick together because when I wrote the problem, there was an extra paragraph about they hadn't seen each other, so they were very lonely, and then they saw each other, their sister, and they were excited, and they hugged on. And I'm like, it's 3 a.m., I need to cut this short. So I simply said they hugged and held on, or stuck. If it's stuck, or if they stuck together, am I dealing with an inelastic or elastic collision? Inelastic. Is energy conserved? No. What is conserved? Momentum. Excellent. So, in a way, bear with me for a moment, because I know I've been teaching you how you don't conserve energy. In a way, you do. You have to know the you have to know the velocity of Molly as she collided into Dolly. So it's a two-step problem. The first part is, well, what's the velocity of Molly at the bottom of the hill? If she started with no friction, no velocity at the top of a hill, the energy initially is mgh, the mass of Dolly. Dolly's final energy, or actually, you could write it either way. Stop it. 1/2 mv squared. So the energy at the top of the hill is the energy at the bottom of the hill. So the m's cancel, and we have 2gh is equal to v squared. Square root of 2gh is equal to v. So Molly's velocity the moment before impact is 20 meters per second, which is actually frightening to see a 100-kilogram panda coming at you at 20 meters per second. That would be pretty frightening. Now, one of the things that we got to do now is that we got to figure out the velocity after impact. It's an inelastic collision, so immediately I write momentum initial is equal to momentum final. The first step, from there to there, energy was conserved because, was there a collision? No, there was no collision, so you could conserve energy. Now we're dealing with the second part of the problem, how energy is not conserved, how momentum is conserved only. Momentum initial. Well, momentum by definition is mass times velocity. So it is m Molly, velocity of Molly, equals momentum final, mass of Molly plus mass of Dolly, velocity, and I could call it v sub f, the final velocity. Because they stuck, technically we're dealing with the Molly-Dolly mass. How do you get the total mass? You just add them up. So the final velocity after the collision, 120, 100 plus 100. So I mean, this really isn't shocking in terms of numbers. The final velocity is 10 meters per second. That after the collision, and it kind of makes sense. One object's momentum becomes an object that is twice as big. So if the mass doubles, the velocity has to get cut in half. Now there's one last thing, just to prove that energy is not conserved. Let's say it was. Well, what is the initial energy prior to collision? Well, it's only the kinetic energy of Molly. So 1/2, 120 squared. So 50 times 400 is 20,000 joules. Energy is measured in joules. The energy final is 1/2 mass of Molly plus mass of Dolly, V final squared. So 1/2, 100 plus 100, 10 squared. 200 divided by 2 is 100. 100 times 100 is 10,000 joules. The energy initial is greater than the energy final. Or you could even say the energy initial divided by energy final, which is greater than 1. And you can play with the ratios. Where, yes?
So that's part of the problem proving that, like, that we're working.
Yeah, I did. This would be where the problem ends. This is the proof that allows me to yell at you guys and say energy is not conserved. Because there's still people who doubt. I can promise you someone on the test is going to conserve energy, and then I'm just going to twitch. Where did the 10,000 joules go? Friction, transformation of shape. The pandas go from full expanded shape to now compressed panda. The sound of two pandas hitting each other is rather spectacular. So you have to remember that the energy did go somewhere. Now, one last thing. Energy that I'm talking about is mechanical energy, the energy that you can keep track of. There is a theory, we'll talk more on this on Thursday, energy technically can't be created or destroyed, but what I've really been talking about here is the energy within the room, the local experimental energy. We'll go more specific on Thursday. Thank you.